So the two complexes that I'm going to look at are NiCN4. This has a 2 minus charge. And the other one is NiCO4. So let's go through and look at the requirements. Number one, they both have a coordination number of 4. The CO and the CN are both what we call monodentate ligands, which gives us a coordination number of 4. We have a strong field ligand in each case. So that meets our first requirement. Nickel, if you look on the periodic table, is element number 28. So this is a 3D transition metal in each case. So we meet the strong field ligand requirement. We do not meet the 4D, 5D transition metal requirement. The last one is, do we have a D8 case? And for this, we have to look at the electron configuration. And one of the things that I really want to point out is when we compare an atom versus a cation versus a complex, these are very, very, very different scenarios. A nickel atom is completely different from a nickel 2 plus cation, and that's completely different than a nickel 2 plus cation surrounded by 4 cyanide ligands. Completely different instances here. And we have to treat them differently, and we have to analyze these guys in a little different way. So nickel as an atom, it's all by itself, all in its lonesome. There's no other external, forces or anything acting upon that. You have one nickel atom that's isolated. Its electron configuration is going to be argon, then 4s2, 3d8. The next situation we have to look at, so this is a nickel atom. And this is kind of the electron configurations we learned in Chemistry 121. If we have a nickel 2 plus cation, we're going to go over this a little bit later in the lecture today, but we said that whenever a cation forms for a nickel 2 plus, it's going to fill in the d electrons first, then the s electrons, or it loses its s electrons. So in this case, it's going to be a 3d8 electron configuration. If nickel is in a complex, it's surrounded by 4, in this case, 4 ligands. So if I'm a nickel and I'm just a nickel atom, my electrons are going to fill in the lowest energy possible and fill in all those orbitals. But if I'm a nickel, I have a big s orbital that's spherical. I have d orbitals that are various shapes. If you kind of poke in ligands around me, my energy is going to be a little bit different than if I'm just an atom all by itself and I don't have anything else overlapping with my orbitals. So if I'm a nickel atom, I have my d orbitals that are pointing out into space. If I bring a ligand in, remember way back when we started talking about bonding, bonds form when orbitals overlap. And when those orbitals overlap, it's going to dictate the different energies of everything. So anytime nickel is in a complex, whether it be 2 plus or whether it just be nickel, in this case, if nickel is in a complex and its oxidation state 0 or it doesn't have a charge, we're going to have a 3d10 electron configuration. I'm going to come back to why this is at the end of lecture today. But in this case, we have a 3d10 case. So if we look at the nickel 2 plus in the NiCN4 2 minus complex ion. In this case, we have a D8 electron configuration. In the nickel carbonyl complex with the 4 CO ligands, in this case it's going to be D10. It is not S2D8. So because of this, the carbonyl complex does not meet the criteria to be a square planar, and as a consequence, this will be a tetrahedral molecule. In this first case with nickel with cyanide, we have a strong field ligand and a D8 case. 2 out of those 3 requirements are met, so this is going to be square planar. And this is how you would investigate and analyze some of these complexes where they could potentially be a square planar versus a tetrahedral molecule. One of the things that we also have to look at, and a lot of the times when we look at these coordinations, ML4 is very common, and also ML6. And sometimes just looking at the number of the subscripts on a particular ligand can be a little bit misleading.